Let's see here. Can everyone see this?
Yeah, we can see it.
Okay, so what I just wanted to do is sort of wrap up and discussion. Oh, sorry, the talks, and then a few minutes only, and then some of the questions that popped up during the talks, and also yesterday from various sources. So I think a summary of the talks today show that we have made significant progress in this part of the phase diagram in recent years. And I think that what has really driven this the field for the past 5 years or so is the lattice results. So if you go back to almost 2 decades, lattice results for finite isospin did exist, but they were not sort of high precision as of today. So I think that this has been a sort of driving force in the field, and I think it's an area where we can make comparison with models and low energy effective theories. And I think also that the talks today show that there is, at least t equals 0, there's good agreement between models and KPT and lattice. Then the interesting application that Bastian mentioned at the university, we have pion condensation there. How can you sort of detect it via gravitational waves, etc.? That seems to be an avenue for further exploration. Then we had a couple of talks on inhomogeneous phases, superconductivity, and some of those issues also sort of are related to this session on, I think it was Tuesday, that was specifically on inhomogeneous phases. Then I would like to show the phase diagram. It's reminiscent of, or an earlier version perhaps, of what Bastian showed today. That's the one to the right, and the one to the left is the one I already showed in my my talk. And there you see the green line, which is the crossover, also which is the transition line between the pion condensed phase and the other phases in the UIT plane. It's pretty much vertical all the way to this tricritical point, and then it levels off very quickly. To the left, I have indicated this Bcs Transition. This phase diagram is basically a copy of another figure of the lattice group. And that line is one of the questions that we might want to discuss in the Bcs transition. So here are a few questions that Bastian raised yesterday. Now the phase diagram to the right is based on lattice results, and you can see a model calculation here where the green line is again the transition to Bose condensate, and that is really reproducing extremely well the behavior of what you see on the lattice. Here also sketched is the Bcs transition, and the criterion here is basically that the chemical potential μI is larger than the quark mass. So as you crank up the isospin chemical potential, the quark mass decreases, and then at some point it exceeds it. And then that's at least the model calculation that has been a common definition of the transition line between the BEC and BCS. But anyways, how to look for it on the lattice is certainly an interesting question. Then other interesting question: transport and quasi-particle properties in the BC phase. What about inhomogeneous phases? The combination of isospin and magnetic field on the lattice, There was also a talk on that on Tuesday by Thomas Brauner, where it seems that under certain conditions, those theories are also free of the sign problem. More specifically, if you choose the charge to be the same of the UND quark, then you can sort of avoid the sign problem. If you will stick to real QCD, then I'm not sure whether you can do some expansion around 0B field, then perhaps you can probe this part of the phase diagram. Then on the other hand, Chi-PT gives you beautiful vortex lattice structures like this. So it's clear that when you turn on the magnetic field, it's not really clear what will happen. But interesting, certainly, if there's any way that you can see some of the inhomogeneous phases on the lattice. So that was sort of a summary of what's talked today, and a bit about certain direction you can think of going into. Then let's see, I will now stop sharing, and then I open for discussion.
So I don't know, Dmitry Voskresensky wanted to make a comment, I don't know, maybe.
Yes, please.
Do you hear me?
Yes, yes.
Okay, it's fine. So I have a few comments and then questions. First comment about baryon-rich matter. Pion condensation in baryon-rich matter was considered in connection to nucleon matter many years ago by McDowell and Brown, Bain and others. It was shown that S-wave condensation cannot exist because of Weinberg-Tomazawa repulsion. Only P-wave pion condensation in nuclear matter may exist with non-zero chemical potential. And this I did not hear about today. It was shown that this repulsion is less important for counts. So count S-wave condensation was discussed a lot, also as P-wave condensation, but pion condensation considered only as P-wave. This is first. Second remark is about baryon-less matter. Do you hear? Hello?
Yes, yes.
Fine. About baryon-less matter. Veronica asked a relevant question that isospin chemical potential in baryon-less matter is very small. There is an answer for that, which was not discussed today, that due to non-equilibrium conditions, heavy-ion collisions, initially the system may be prepared as overpopulated system. But then there appears question how important are absorptive processes and elastic processes. And also many years ago by Gerber and Leitwiller, and later it was shown that elastic processes are dominated. So there is some time step when one may consider non-equilibrium growth of chemical potential of pions during the cooling process. And there appears bosonization, which is seen actually in enhancement of pion distributions, momentum distributions at small momenta, and also maybe in pion condensation. Pion S-wave, pion Bose-Einstein condensation, not such as in baryon-rich matter, but another one. Also, resonances decay at the initial stage, and also they give some contribution to this non-equilibrium situation. As well, also in rare but nevertheless possible events, in event-event collisions, there may appear systems with Pine systems with large multiplicity. So these are reasons for, maybe the reasons for, at least in such collisions, in some collisions will be essential non-zero chemical potential. This is second remark. Then remark about what Minarelli told about multi-meson condensation. I didn't see the self-interaction term. And it was also many years ago shown that when you take into account, for instance, lambda 5/4 term, then the most energetically favorable structure will be running wave, and not several condensed amplitudes included together. So I would like to ask whether this self-interaction was taken into account or not. If not, then it's necessary to take into account this, and then I think that it will be in favor of one condensate instead of several. Now maybe two questions which I did not understand. First question that I think in Brandt talk, it was shown the energy as function of the temperature, which is negative and has minimum at finite temperature. And my question is how it can be. It is, at least naively, it looks like perpetuum mobile, because ground state is always state with zero temperature. And second question about what was discussed by Minarelli about, maybe I misunderstood, but as I understood that he said that electron chemical potential allows to produce Pine condensation without baryons. But then again, the appears question about the energy, because why then to keep Pines, because then the system should be electrically neutral. So as a response for electrons should appear pi plus, but why then they not to decay to positrons and neutrinos? And then the appears question, what is energetically more favorable? And so this question was not raised. So these are questions, maybe in discussion, the authors will answer them. Thank you.
All righty, let's see. I think there were several questions here. Bastian, do you want to comment on the temperature stuff?
Well, I mean, so I'm not quite sure what you mean. So what I showed was at some point that at t equals 0, the interaction measure becomes negative. That's true. That's what I showed. That's what's happening. But that's fine. But the energy density never becomes negative.
So it was some energy as function of the temperature, and one of the last.
Well, I mean, well, okay. So maybe I can share my screen, and you can tell me where it exactly was, and then I can answer. That is fine.
Maybe I missed the talk, and it was a different talk. But okay.
Let me share my screen.
It was not the case that okay.
So here, this is the equation of state at non-zero temperature, but here also the lines at zero temperature.
No, it was just several lines with minimum at finite as function of the temperature.
You mean this one? There is a function of a temperature.
No.
No, well, I don't.
But okay, maybe it was in a different talk, and.
No, but from here you can see that the energy density never becomes
Mm-hmm. Okay.
This
Then,
will remain true.
I just didn't look it carefully. So thank you.
Okay, so there was also a question for Massimo. Do you want to answer that question?
This was question about boson stars, which you discussed.
Hi, yes, I'm here.
All right, great. Do you want to make a comment?
Sorry, can you repeat the question, please?
If I understood you correctly, that you considered the system without baryons and said that if when chemical potential of electron becomes large, then there may be a charged pion condensation, and such a system can be realized as some boson star. But then my question is that since the big system should be neutral, then there are many these pi classes, and why not them to decay to positrons, and then electrons together with positrons will radiate and come to zero energy state. So then initially your state with pion condensation should have negative energy. But in electrodynamics, where other interactions are not included, like nuclear interactions, for instance, and if you have electrons and pions, you have only electrodynamics interactions. There is the theorem that the energy is always positive. So my question is that how can you energetically to show that such system is more energetically favorable than the system which decays just on radiation?
Yeah, the thing is, well, up to now, this is kind of a toy model, right? I mean, in the sense that even if we have some soliton solution, solitonic solution of the system, still, I mean, we do not have really baryons inside, so we don't have nuclear matter. Okay, and the important effect actually should be of I mean, there's many ways in which nuclear matter interacts with pions, and you know, in the early works, it was claimed that actually was that one of the way to drive meson condensation and so on and so forth. Still, I mean, in my in the solution that we have found, actually, there's a kind of energy cost for producing a soliton. Okay, if that's what you mean. So in the inhomogeneous phase, there is I mean, the solitons are protected by their topological charge. So once you create them, they do not actually decay. But the thing is that actually one should improve this decretion introducing real baryons. But that means a big complication of the system. I don't know whether I answered your question.
No, of course not, because just the question was, did you calculate the energy of the system? And the energy should be negative in order the system would be stable. If it is positive, then it appears another question that it can radiate energy, maybe, and to decrease energy. So one should check at least, even in model, did you take into account all channels of radiation into account, and is this system stable or not?
Massimo, do you want to?
Yeah, well, I'm a little problem. A little problem here because I'm with my small kid and I cannot. Maybe you can hear him in the background. He doesn't like much your question, actually. No, the thing. I'm sorry, I cannot answer now. I will email you the answer. I'm sorry.
No.
Yeah, he's 7 months old. Yeah.
Okay, just mute yourself for the time being. And then I see that Gergo and Rodi has raised his hand.
Yeah, I wanted to go in a different direction, but maybe a comment on the previous question is that the critical thing is that one has a large chemical potential for the neutrinos, in that these pions would decay. So if you have a pion decay, then you produce a positron and a neutrino, but you cannot, this decay is blocked because there are already very many neutrinos around. So this has been discussed by Tomáš Brauner actually, and Abuki, I think, a couple of.
This I disagree, because neutrinos have very large path lengths, so they go off the system, so they have no chemical potential in this. By direct reactions go off.
That's true, and that's why you actually have to go back in time to the early stage of the early universe. So you have to go to the early universe actually, where also high temperatures are around and neutrinos can be trapped. This we discussed can be the case above 10 MeV temperature, and then you can consider a neutrino cloud where neutrinos are trapped, and in that cloud you can form pion condensates.
Let me motivate without neutrinos.
Wait a second. Gergo, you wanted to said you go in another direction, you said?
Yeah, actually, but so that would be like more in the direction of what is
that?
No, now you have to wait. Now it's Androdi speaking.
Yeah, thank you. So I was wondering, because many of the audience actually shared from the previous sessions where magnetic fields were discussed. So I thought maybe this is a good question to ask. In the case of magnetic fields, we have learned that lattice and models give very, very different results. And in this case, for the isospin chemical potential, we somehow see that the results are very, very similar. And so in the case of the magnetic fields, there was something to be learned from this discrepancy. In this case, with the chemical potential, we don't see this. So maybe I thought it's a good idea to try to understand where the two different kind of behavior comes from, and what we can learn in this setting from the comparison between models and lattice results.
Let me comment without any chemical potential and neutrino Pauli restriction principle. Even for one nucleon, when we take into account Skirmy model, even for one nucleon, we have inhomogeneous condensate. And this object lives, order of lives, is the neutron lifetime, 50 minutes. So in the condensate states, pions can be stable in the order of lifetime of minutes, 15 minutes neutron lifetime. So condensate and free neutron is different things. This one. And in stars, there are ingredients like Pauli restriction principle and forbidden principle and chemical potential. If there are neutrinos condensates, for example, who knows, maybe neutrino also condensates. Okay, let's comment in the more simple example case of nucleons as inhomogeneous condensate of pions, the minimal one, with baryon number 1. We could not imagine less simple system for the inhomogeneous condensates for pions. Thank you.
All righty. So this question that Gergo raised about isospin and B field, I don't know whether some of the people who have been working on Prabal at ICAR, do you want to make a remark on this, or?
Yeah, so I think, I think there is, there's some interesting differences between the lattice work and the way I approach the problem. And I think the difference is roughly the fact that on the lattice, both the magnetic field and isospin are simultaneously present. So if you're in the normal phase, and you have a magnetic field turned on, the pions have a magnetic mass, not the vacuum mass. So as you start tuning the isospin chemical potential higher and higher, the phase transition line shifts because the pion mass is now the magnetic mass. The difference in the way I approached it is I said, okay, well, let me tune the chemical potential such that the system is already in the superfluid phase. And then when you try to put in the magnetic field, if the superfluid is charged, it becomes a superconductor. So you can't do that, right? So there is this sort of inherent inconsistency in trying to have a uniform magnetic field when you have a charged superfluid. I think from an intuitive perspective, I think one issue I think that I would like to understand, and maybe there are some insights in the room, has to do with the fact that there's a diamagnetic phase observed in the lattice at close to mu I equals m pi, but there are no pions. So I'm wondering what the mechanism by which a diamagnetic phase forms when there isn't a density of pions to create supercurrents to get rid of this external magnetic field. So that's one sort of aspect of the problem that I don't think I fully appreciate, but I've seen this in the context of, for instance, the linear sigma model with a chemical potential and the magnetic field turn on. Something similar happens. But intuitively, I don't feel like I understand exactly why that happens.
Anyone from the lattice community want to comment on this? Or I don't see any raised hands, by the way, so I'll just again share my my screen. So there you see the possible possible phases in the mu-I B plane. So a specific question to the lattice people. Let's assume that you would, or how realistic is it to investigate inhomogeneous phases for non-zero B?
Yeah, maybe I can comment on that.
Yes, please.
So that's a good question. That's a good point that Prabha mentioned, that there's this non-commutativity of the two limits, whether you first consider the B and then the pions, the chemical potential, or the other way around. So, and that's also something that you said, Jens, that on the lattice we might set the two charges of the quarks equal, and then there is no sign problem even if there is a magnetic field and the chemical potential present. But of course, in that setting, you have neutral pions because up and down quark charges are said to be the same. So a U bar D has zero charge, and that is a completely different setting compared to the charged pion condensate that one has when the physical quark charges are used. So we have to stick to that, and in that case, there is a sign problem, and you cannot go you cannot include both the magnetic field and the isospin chemical potential. And one more point about that on the lattice is that magnetic field is also quantized. It's not a discrete variable on the lattice, and that's actually the biggest problem, that you cannot include the magnetic field like in a smooth way to consider a small magnetic field because of this quantization problem. You have to basically make a jump to a system with unit flux or 2 times unit flux, and therefore approximations don't work. So we are actually trying to find workarounds on this problem, to how to consider both the magnetic field and the chemical potential, but it's not a simple problem.
Okay. See, I don't see any other raised hands. So then there's the question that Bastian raised about the Bcs transition. So let me perhaps play it back to you. Sort of, how would you look for such a transition on the lattice?
Right. Yeah. So I mean, well, since you asked me, I mean, I can actually show a slide on this.
Yes, please do.
Basically, so I actually had this slide in another presentation. I just have to, just a second. I have to see what it is exactly. No, there is that. Probably in the wrong file now. Sorry, it's taking a second longer than I thought. That should be, here it is.
Okay.
All right. Okay, so am I, oh, sorry, somehow that's not working well. What am I doing here?
Maybe can I ask a question in the meantime?
Yeah, just do
Yes.
that. I'm trying to share screen, but
So
didn't work.
Jens, you said that that you had this definition of the BEC-BCS crossover, and you said that that comes from the fact that the constituent quark mass, I assume the constituent quark mass is larger than smaller than the isospin chemical potential.
Yeah.
Right.
Yes.
So can you somehow argue why this is a good definition? And
I guess if you think of if you come from the, let's say, non-interacting direction, then I guess you could say, okay, there's a formation of a thermosphere. That's sort of the picture we think. That if you have no interactions, then you have a thermosphere. If you have mu I larger than whatever mass of your fermion is, and then you slowly turn on interactions, and then you'll form weakly bound Cooper pairs. And then if you go down in isospin density, these weakly bound Cooper pairs somehow turn into pions. I think this is this BC-BCS thing is sort of has an analogy in atomic physics, but people also are looking at these transitions, I think, via Fishback resonances. But I think that's the picture I recall that people are having.
And do you have a suggestion how to implement this on the lattice?
I have no idea.
Because what we can calculate are densities and then condensates.
Yeah. Okay. Well, maybe there was some discussion about this in a slightly different context. Now I see that Thomas Brauner is not around, but if I remember correctly, some years ago there was some two-color lattice simulations, and then it was discussion about die quarks. But then I think the lattice people used some the behavior of the equation of state at t equals 0, that it sort of was looking reminiscent of a free Fermi gas. So you simply look at the equation of state, and it's not too different from that in certain regimes. And then you said, okay, I think then you could find some criterion based on that. But I don't remember the details.
Yeah, I think I remember this, but sort of I sort of always thought that's a bit indirect way of.
It is indeed indirect. Yeah. Okay, Bastian, have you a figure?
Yeah, I have it. Sorry, that was harder than I thought. Okay, so I could share.
Yeah, please.
And well, let me just do that presentation mode. All right, so what you can see here is, well, I mean, so that's also one of the conjectures, right? That, I mean, this, sorry, let me make that small, and that one. So if you actually, well, if you look at the difference between the Bose-Einstein condensed system and your BCS phase, then typically what we think what the difference is some sort of deconfinement taking place. So we actually look at the deconfinement phase transition and try to figure out whether that goes on into the BEC phase or not. So that's one of the typical things that one can try to do. And that was actually one of my questions, whether this naive picture is actually true, and whether there are like confirmations of this picture, or are there arguments against this. So what we tried to do, on the other hand, to shed more light on this, was to look at an extension of the Banks-Kesher relation. which was derived in the infinite volume limit and the zero mass limit, so zero quark mass limit, and for large mu I. And well, so this extension actually relates in this limit the BCS gap to the density of the complex eigenvalues of the Dirac operator at 0. And well, so what we are having is, of course, non-zero pi mass. We're also not in the infinite volume limit, of course, and unfortunately not at very, very large mu I, but still we try to look at this eigenvalue density at, well, in this case at MUD, which is the light quark mass on the lattice. And then what we found was a behavior mostly like this. So we saw that this parameter, or this density here, is actually quite sensitive to the phase transition, to the Bose-Einstein condensed phase. But then we sort of observed a leveling off. And of course, so the unfortunate thing is that this is the region where lattice artifacts are setting in. So we are not, and this is what is work in progress. So we are not quite sure whether there could be a plateau here or something which raises again, but then these lattice artifacts have the tendency to actually destroy this signal. So to get the eigenvalues away from this point, mostly that's something that we know. And so then the question is, what can we do here? And clearly we can go to final lattices. We can also then go to larger mu I once we have final lattices. And there are a lot of things to do here. But this is one way that we try to approach this. We also think that it is a worthwhile thing. However, there are also these limites. So it would be nice if there would be a method that one could use without taking these, well, without sort of having to rely on this interpretation, which is correct only in this limites. That's actually the way that I should say it. And that's why I sort of raised this question, whether there are any other smoking gun signatures for the existence of this BCS fix.
Okay, so let me just, if you look at your upper, could you please share it again?
Ah, sorry.
Yeah, no, it was just I had sort of a remarkable question to your figure.
Sure. Just a second. All right.
Yeah. Okay. So the upper one. So the red and blue lines, those correspond to the Bcs transition according to some deconfinement criterion. Is that correct?
Right. Well, you mean these lines here? Am I correct?
No, the upper figure.
Sorry. Sorry, here that's our line for the standard Pi condensed phase, right? The Pi condensed boundary, yes. And this red line can be translated to the deconfinement transition line. Yes. Okay. So let's say if you extrapolate to larger values of mu I, is there any chance that that would hit the t equals 0 or the mu I line? Well, I just seriously cannot tell because I don't have any lattice data there. I mean, it's even hard to tell what the curvature would be, right?
Okay.
So,
yeah.
I mean, I really cannot say anything. Sorry.
But can I make a comment about this?
Absolutely.
So, so there is a study by Sen and Cohen at high isospin chemical potentials, right? So there's a BCS gap as asymptotically large isospin chemical potentials. So since there's a BCS gap, if you're below the gap, you can write down the effective theory, which is a gluonic theory with modified coefficients. And we know that for a purely gluonic theory, the transition, there was a deconfinement transition there below the gap. So we know, at least in the asymptotic regime, that this transition has to be there within the if you like, the Pi condensed phase. So that's a model independent argument for why the deconfinement phase has to be within the Pi condensed phase. Obviously, that doesn't guarantee that it is in here away from the asymptotic limit, but at the very least for large isospin chemical potentials, we can be fairly certain that that's the case.
That's actually a very good point. And again, a similarity to the magnetic field case. Also in the magnetic field case, if you go to very strong B fields, then you can derive an effective theory, which is a pure gauge theory, and then it has a first order phase transition. And also here is the case. And it has not been explored into too many details so far, but I think that's actually a pretty interesting project to look at this high isospin limit deriving really the coefficients of the effective theory and maybe even simulating it on the lattice and then seeing whether there is really a first order phase transition.
Yeah, I totally agree.
But as to what extent that transition is really connected to this red line, which Basti is now showing, that's another question of interpretation. So
yeah, that's not very clear actually. Yes. So.
And it turns out that one of the scenarios that San and Cohen point out is a scenario that Jens was referring to, where the line goes to the t equals 0, limit. So again, it's a plausible scenario. It has to be somehow checked explicitly, and it's not clear exactly how one does that.
So as I said earlier, right? I mean, for the lattice, we just have the problem that we cannot go like far in this direction actually, unless we go to very fine lattices, making it harder. And then of course there is the chance maybe of coming from the other side, as Gabriel has just said, but still it would also from this side be very difficult to reach this intermediate region, right? So that's one of the tough things to do here, basically, I would say.
Right.
Can I have another question to Prabal?
Sure.
Yeah, should I stop sharing or?
Yes, please.
Okay.
So you said that you are considering this superconducting phase in the presence of the magnetic field, and then the magnetic field is expelled. Then you can, I guess, calculate something like a penetration length if you consider the photon to be dynamical. Can you do that?
Yeah, so the penetration length scale goes like the inverse of the photon mass, right? If you look at the coefficient of the photon field, the quadratic term, you can absolutely calculate this. I don't think I did this in my letter, but I may have notes that already does this. And if I recall correctly, I think Massimo has a paper that I think may have this quantity explicitly stated as well. But yeah, but it's calculable.
Yes, I did actually.
Okay.
And how does it depend on mu I? Or is there dependence on mu I?
Yeah, it does. Of course, it vanishes at the phase transition point.
So I think it probably goes like sine alpha or something like this.
Right, exactly, sine alpha. It's basically what you get gauging U1, all right? So you gauge U1 and you have that the term which is proportional to mu I squared becomes a mu squared times sine square alpha. It's one of my paper, I think. Maybe it's on the review as well.
All right, interesting. And then something else again to Prabal. Sorry if I can ask again.
Yeah, sure. Go ahead.
You said that there are these two different scenarios, whether you can have a type 2 condensate, depending on whether E times F pi or M pi is bigger. So which of the two is now the conclusion? I think I missed.
The conclusion is for real physical parameters, E F pi is less than M pi. It's primarily because E is so small. And so for this reason, for real physical parameters, the system is always type 2. But obviously, if you choose the quantities in a different way, you could have EF pi be bigger than M pi. But type 2 superconductivity happens only if mu is bigger, magnitude of mu is bigger than EF pi. So you could have, for non-physical parameters, in the condensed phase, both types of superconductivity.
Okay, let's see now. We've had a lively discussion on large mu I and MB. I don't see any raised hands at this point. The question is, have we covered all the questions that were raised? Now
I have one question, Andersen, if I can.
Yes, please.
So I would like to understand a little bit more about these low energy constants that it is necessary to fix in KPT.
Yes.
I'd like to understand if there are some criteria to fix them, or it's arbitrary, because the results strongly depend on that also.
No, it's what you do is that you calculate the pion mass in the vacuum, And of course, at tree level, m pi is m. But then you have loop corrections. And then you must tune m and f to get the physical values m pi and f pi. Once you use your low energy constants that you have obtained from experiment. So there's no okay. Of course, there is a uncertainty in the low energy constants that you measured. But apart from that, there is no ambiguity or slack of any kind. It's really fixed by, in our case, one loop calculations in the vacuum, and that's what you have to do in order to perform a consistent calculation at next to leading order.
All right. So if I can, I have other question for people from the lattice and people from the models.
Absolutely.
So I'm finishing a comparison with SU3 NGL model with lattice results and also chiral perturbation theory. And there is one thing that reading your papers, Prabal papers and your papers, SU2 is, especially at low temperature, is doing a best job than SU3 compared with the lattice. This is also happening with my NGL results, and I'm trying to understand what's the physical reason that behind this. So in this same way, I would like to ask it to Brandt and Gergo, how they treat S quark on the lattice, because it can be related with our predictions with SU2 fall above your results. And your results, if I understood, are SU3, right?
So shall I answer?
Yes, please.
How we treat it? Well, I mean, it's fully included. It doesn't have a chemical potential. But apart from that, I mean, it's just fully included. It has the physical strange bulk mass. So it also has the right mass. And in that sense, we are fully including it in our pure isospin system. So it's not left out. It's fully in there. Does Gergo want to add anything? I don't know, but that's what it is.
I don't think there's too much to add. So I mean, in the case of the chiral perturbation theory, Jens and I think maybe Prabha had this paper lately comparing the 2-flavor and the 3-flavor cases, and I think there is a big difference depending on how you set the parameters.
Yes.
Maybe something related to that.
It's maybe you want to comment on that after me, Prabal, but I think it's you have a number of parameters that you have to fix, but that's not, you cannot do that in a unique way. You have to sort of pick out a number of physical quantities, let's say m pi, f pi, fk, mk, etc. And there are 4 of them, and you have only 3 parameters in your theory. So you have to leave out 1, and that'll in principle be prediction. And that, let's say, if you choose m pi, f pi, and fk, oh sorry, mk, then fk comes out, I think, like 10% off what you would expect. So certainly there is some ambiguity. Secondly, I think that the 3-flavor low energy constants, they come with huge uncertainties. So there's, of course, that's why we have wide bands in our plots. And it's quite interesting. I think it was yesterday in Physical Review D, there was a sort of update of the low energy constants in 2- and 3-flavor Chi-PT. And I think that the 3-flavor low energy constants, they change quite a bit. So we might go back to the drawing board and redo our analysis. Prabal, do you want to chime in?
Yeah, so I can add to that a little bit. So part of the reason for redoing this analysis with the new LECs is because, you know, in the 3-flavor versus 2-flavor comparison, what we showed was that a lot of the difference between the 2-flavor observables and the 3-flavor observables had to do with the fact that the LECs were quite different. So we can isolate most of the difference to the determination of the LECs, and the paper that Jens points out has LECs that are dramatically different from the ones we use. So I think it'll be interesting to sort of compare how the new results look. And the final point is that, I mean, the K on mass is about 500 MeV, and we're using an effective theory at next to leading order, which is good, but that also means that the systematic corrections for realistic strange quark masses is fairly large. It's not a small difference, and for that reason, I think one has to be fairly careful interpreting the three flavor Chi-PT results. They're not as controlled as the two flavor results.
I don't know whether I can comment on this as well.
Yes, please.
Yes, I think I did this calculation some years ago in Canal perturbation theory with three flavors as well. And the thing is that we were convinced that maybe in this case one should work the other way around, like trying to fixing the low energy constants using lattice QCT results. And however, the point is that when you compute the free energy, I mean the energy density of the system, you only have some combinations of energy constants. They are I don't remember. I mean, because you have several of them. They are summed up in some terms. So maybe we can at least fix the sum of these terms, comparing lattice QCD results with Chi-PT with three flavors. So I think, I mean, if one has time, I mean, maybe one should look at this, whether one can get improved combination of low energy constants comparing lattice QCD.
Right. Let's see, Ricardo, did you raise your hand?
No, it was one what with that question. I'll just like a comment this. We will put an archive soon.
Okay.
And NGL predictions now, compared with the lattice, it's SU2 is doing a better job than SU3 for zero temperature. And for fine temperature, SU3 is doing a better job than SU2. This will report soon. Would you like to see from Prabal, Andersen, or Massimo? Do you have estimatives for SU2 and 3 at fine temperature, comparing to the lattice results?
Massimo?
I don't.
Prabal?
So, I mean, Jens, you can comment on this as well, so we put out an archive on finite temperature or chiral perturbation theory, and the difference between the lattice result and Chi-PT result is quite significant, even at low temperatures. And this has to do with the fact that the power counting scheme that we naively think of, where you take a quantity with mass dimension, we say that the systematic corrections are of order that quantity divided by 4 pi f pi. That story doesn't remain true at finite temperature. And so the agreement with the lattice is only valid for temperatures that are relatively low, and qualitatively the results are actually quite different at finite T. But if Jens wants to, if you like to add to that.
No, I'm fine. All righty.
I have a question for the lattice guys.
Yes, please.
Possible? Yeah, for Bastian and Giorgio. It was basically the last question of my talk. Whether you think it's possible to look for inhomogeneous phases on the lattice.
Well, I mean, so since these inhomogeneous phases, when I understood it correctly, you might correct me, are at either non-zero B field or another chemical potential, so we have to include something else, then we typically run into the sign problem. So it's really difficult. I mean, it's really difficult to just go in these directions. But as I said, correct me if I'm wrong and I missed something, but that's typically the case. So in this case, we won't be able to do anything directly due to the sign problem simply, right? So yeah, it will be difficult, but of course we are to some extent thinking in these directions. But yeah.
Can I quickly add to that?
Yes.
So I know that, for instance, Maxim Chernodub, I mean, when he was thinking about rho superconductivity and high magnetic fields, I mean, since this is a zero density problem, looking at inhomogeneous phasing in and of itself is not a problem because you're simply looking for spatial correlations, right? The issue is truly the fact that there's a sign problem that's hard to sort of work around. So the challenge is not on the, looking for inhomogeneous phase side, it's actually on the fermion sign problem side.
Yeah, going there. Right.
Yeah, maybe an additional comment to that. So on top of that you have to deal with the sign problem, you also have to come up with some way to detect these phases. So I mean, in your model or in your model, you have some ansatz, and then you plug it in and you find that it has a lower free energy, and then you know that there is an inhomogeneous phase. But then you can really explicitly just use some kind of field configuration. And on the lattice, in the end, we always have translational invariance, and you have to look at some higher endpoint functions or whatever that are sensitive to these modulations. So that is an additional problem, that you have to use a different technique to detect such inhomogeneous phases, if there is any.
Yes. Okay, we have now almost been discussing for 1 hour, and I know there will be another session later this afternoon/evening. So before I wrap up, there is time for one last question before I close the session.
I have a last question.
Okay, shoot.
To you or to Prabal, if we should also expect the row meson to condense at some point for some large isospin chemical potential, or this is not the case?
Prabal, have you thought about this?
That's actually a really intriguing question. I have not thought about it.
Okay, then I just think we'll leave it here. Before I let Roman take over, I would like to thank all the speakers today for their nice talks, and also for the everyone who's been listening to this session, and to the lively discussion we've had. I think it's been very fruitful few hours. So thank you, everyone.